Hello students. Today with this video I am going to start online classes for your mathematics. Actually we are forced to do online classes instead of offline class because of COVID pandemic. Anyway, I will try my best to make your online learning better. So in this video the chapter I am going to discuss, that is chapter number 1, real numbers. And if you have any suggestions regarding the video or the teaching process, you can give the suggestions so that I can make a better way for your learning. So let's get directly into the topic. In this chapter, there are 5 main topics we are going to discuss. First one is Euclid division lemma. What is Euclid division lemma? It is almost similar to the division of the numbers we have learned in lower classes. We will discuss and fundamental theorem of arithmetic, that is related to the factorization of composite numbers, then HCF and LCM, that is we know very well how to find the HCF and LCM, also the relation between HCF and LCM, but we will recall this topic again. And the next one is that proof of irrational numbers. Proof of irrational numbers, it is a new topic and it's very important one, so we will discuss in detail. And the fifth one is the decimal expansion of rationals and irrationals. This is also we have learned in class 9, but still we will learn some more properties of decimal expansion of rationals and irrationals. Out of these 5 topics, in this video I am going to deal only these 3 topics. The remaining 2 will be discussed in the next video. Okay, so let's start with the Euclid division lemma. What is it state? Given positive integers a and b, then there exist another 2 integers q and r satisfying the condition that a is equal to bq plus r, and the range of the r is given that it should be greater than or equal to 0 and it should be less than b. Let's take an example that let a is equal to 14, okay, and b is equal to 3. So we are going to divide 14 by 3. So we will get a, what is the question we will get here? That is 4, and 3 into 4 is equal to 12. The remainder will be 2. So we can represent that 14 is equal to 3 into 4 plus 1. So this 14 is actually, this 14 is A and 3 is B, 4 is Q, 1 is R. That means A is the dividend. A is called a dividend and B is called a divisor and Q is called a quotient and R is called a remainder. We already learned in lower class that is dividend is equal to divisor into quotient plus remainder. This is same as that one, but here just to be stated in a most appropriate way. Okay, so let's see the some applications of Euclid division lemma. Use Euclid division lemma to show that any odd positive integer is either of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So, very important question. Let's apply the Euclid division lemma that let a be any integer. Let a be any integer, any positive integer, okay, any positive integer, we get and a is any positive integer and b is equal to the value of b we can choose 6 because here it is given in the form of b is equal to 6. Clear? 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5. So in all these three b is given as the 6. So we can choose b is equal to 6. Then by Euclid's division lemma, we will get, I am writing the abbreviation of Euclid division lemma here, okay. We will get a is equal to bq, instead of bq plus r we can write a is equal to 6q plus r because here b is 6. And also in the condition for Euclid division algorithm it is given that the range of r should be greater than or equal to 0 and it should be less than b. That is very important condition given in the Euclid division algorithm. So here b equal to 6, the value of r can be 0, 1, 2, 3, then 4, 5. It cannot be 6. So these are the possible values of r because in the Euclid division algorithm this is the condition stated for the remainder. Okay, then we will get r is equal to 0, 1, 2, 3, 4, etc. So the possible numbers are, so a is equal to 6q plus 1, 6q plus 2 and 6q plus 3, 6q plus 4 and 6q plus 5. These are the possible numbers of this given integer. These are the possible integers. Now we have to show only any odd positive integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5. That means the integer 6q and 6q plus 2, 6q plus 4. These three integers are not in this given list. So what happened to these integers? Let's see. If you divide 6q, okay, what happened? We will get a 6q divided by 2 is equal to 3q. Similarly, 6q plus 2 divided by 2 is equal to, let's take 2 common outside here. So 2 into remaining here it will be 3q and plus here it will be 1 divided by 2. 2 to cancel, we will get a 3q plus 1. Similarly, in case of 6q plus 4, divided by 2, what we will get here? 2 we can take again outside, so 2 into here remaining 3q plus, in the place of 4 there will be 2 divided by 2. 2 to again cancel it, we will get a 3q plus 2. So what actually means is that this all integers 6q plus 2 and 6q plus 4, these three integers are exactly divisible by 2, which means they are even numbers or even positive integers. That means here we have to show only any odd positive integer, therefore this number should not be in the list of odd integers. Since a is odd, a can't be 6q plus 1 and 6q plus 2 and 6q plus 4, since they are divisible by 2. Therefore any odd integer, any odd positive integer, okay, negative integer is not applicable. Any positive integer is of the form is of the form. What are the remaining numbers here? 6q plus 1. Okay, 6q plus 1 and 6q plus 3, and the third one is 6q plus 5. So these are the possible numbers. So hence it is shown. Okay. Now let's take another example. Use Euclid division lemma to show that the square of any positive integer either of the form 3m or 3m plus 1. Same procedure what we done in the last question. Let a be any positive integer and b is equal to 3. Why b is equal to 3? Because in this form b is given as 3. Clear? So we are choosing b is equal to 3. So then by Euclid division lemma we get a is equal to 3q plus r, where r is equal to 0, 1 and 2, because it should be greater than or equal to 0 and greater than or equal to 0, and it should be less than b. Therefore, r, the possible values of reminders are 0, 1, 2 and 3. So therefore, the integers are, so the integers a is equal to 3q plus 1 and 3q plus 2. Here remainder is equal to 0 because of the 3q plus 0 will be 3q itself. Clear? Now square of integers. First let's take when a is equal to 3q. What happens when a is equal to 3q? A square is equal to 3q whole square. A square is equal to 3q whole square. That is equal to, what will we get? 3 into 3. 3 square is 3 into 3 into q square. Q square we are writing as it is. That is equal to, what happened? 3 into 3q square? 3 into, for 3q square, let's substitute as m. So we will get a 3m. Since 3q square is equal to, it will be another integer, m. Okay. Now let's take when a is equal to 3q plus 1. That is the second position. This number we done, and the second number is 3q plus 1. A square is equal to 3q plus 1 whole square. That is equal to, how to expand this one? What is a plus b whole square x plus y whole square expansion? The identity we have learned, that is x plus y whole square is equal to x square plus 2xy plus y square. Using this algebraic identity, we can expand this. So we will get 3q whole square plus 2 into 3q into 1 plus 1 square. That is equal to 3q whole square we already expanded here as 3 into 3q square. So we can write it as 3 into 3q square plus 3 into 2q into 1 will be 2q. We are writing 2 into 3 into 1 as 3 into 2 itself. Okay, we are rearranging that one. Plus 1 square is 1. 1 square we are writing it as 1. So we get 3 into 3q square will be like something over. Okay. Now see here, in first term also 1 3 available, and in second term also 3. What we will get here? 3 into 3q square plus 2q plus 1. Okay. See here, 3 we taken outside, the remaining terms we written here. That is equal to 3 into The entire term 3q square plus 2q we are substituting as m. Then the remaining 1 here. Since 3q square plus 2q is equal to m. Because for m any integer can be applied. The question is actually incomplete. You can see in your textbook 3m plus 1 4. Question is for some integer m. That is m can have any value. Okay. Now the next number, the last number we are going to take, that is when a is equal to when a is equal to 3q plus 2. In this case, see, a square is equal to 3q plus 2 whole square. Here also we are going to explain, or we are going to expand by using the same identity, a plus b whole square. So we will get a 3q whole square plus 2 into 3q into 2 plus 2 square. That is equal to 3q whole square we expanded in the previous two steps, that is 3 into 3q square plus 3 into 4q, because we are writing 2 into 3 into 2, 3 writing first, then 2 into 2 is 4, plus 2 square is 4. 2 square is we have written as 4. Seems like 2 square is equal to 4. But the problem is that we don't have any option like 3m plus 4 in this question. So we have to modify this 4 into the available option. So for that we can again modify this 3 into 3q square plus 3 into 4q plus this 4 we are going to change that, and we are going to write as 3 plus 1. Now see here, in all these first 3 terms, 3 is common. Here 3, here 1 3, and here also 1 3. So let's take that 3 outside. So we will get 3 into 3q square plus 4q plus, when these 3 taken outside there will be 1, plus one more 1 is there outside the bracket, which is equal to 3 into 3q. For this entire term substitute as m, so we will get a 3m plus 1, since here 3q square plus 4q plus 1 is equal to m. That is what we conclude. So now we represented any integer, positive integer, in the form 3m plus 1, and here also see we represented the form 3m plus 1, here it is 3m. That was the question, 3m or 3m plus 1. This question is saying that show that cube of any positive integer is either of the form 9m plus 1 and 9m plus 8. So same as done in the last two questions, let a be any positive integer and b is equal to, according to the last two questions, we could take that 9. It should be 9. But the problem is that if you take b is equal to 9, then you will be having numbers like 9 cube, 9 cube plus 1, 9 cube plus 2, etc. up to 9 cube plus 8. So we have to find the cube of all these 9 numbers. So it will be quite long. So we are not going to take b is equal to 9. So we are going to take a smallest number in which the cube of that number is a factor of 9. For example, 3. What is 3 cube? 3 cube is equal to 27. So that 27 is actually 9 into 3. So even if you are taking b is equal to 3, while we taking the cube, we will get a 9 as a factor, so that we can represent this one. Because of that, we are going to choose the value of b as 3 in this question instead of 9. Clear? So what will we get? Therefore, then by Euclid division lemma, we will get a A is equal to 3q plus r, where r is equal to 0, 1 and 2. So A is equal to 3q, 3q plus 1 and 3q plus 2. Now we take the cube of integers. Cube of integers is equal to, when A is equal to 3q. When A is equal to 3q, we will get a cube is equal to 3q whole cube, which is equal to 9 into 3q cube, because 3 cube we can represent as 9 into 3. That is equal to 9, the entire term 3q cube. Okay, so we are going to substitute as 9m, since 3q cube is equal to m. Here we substitute 3q cube as m. Now let's take the second possibility. So first we had done in case of 3q, next 3q plus 1. So what we will get here? When a is equal to, when a is equal to 3q, what we will get? 3q plus 1. Then a cube is equal to, a cube is equal to 3q plus 1 whole cube. That is equal to, here the problem, it is in the form of x plus y whole cube. What is the expansion of x plus y whole cube? We know that x plus y whole cube is equal to x cube plus 3xy into 3xy into x plus y plus y cube. This is the algebraic identity which using for the expansion of x plus y whole cube. So we will get here same as 3q cube plus 3 into 3q into 1 into 3q plus 1 plus 1 cube. That is equal to 3q whole cube is we already written as a 9 into 3q cube. So 9 into 3q cube plus 3 into 3, we can write it as 9. Am I right? 9 into q into 3q plus 1 cube is equal to 1. Now see in these two expression, here in this in these two terms, first term as well as in the second term also 9 is common. So let's take that 9 common. What will we get here? A cube is equal to, this 9 take it outside, so 9 into remaining here 3q cube and q into 3q plus 1. So 3q cube plus q into 3q plus 1. Okay, so this bracket should be like this, plus last outside the bracket one more 1 is there. That is equal to, substitute for the entire term, for this entire term substitute as m. So we will get a 9 m plus 1, since 3q cube plus q into, this is not 9, okay, q into 3q plus 1 is equal to m. So now we are represented in the form 9m as well as 9m plus 1. Okay, now if you take when a is equal to, next when a is equal to 3q plus 2 whole cube, you will be getting whole cube, okay, not whole square, whole cube, you will get in this form 9m plus 8. Just to simplify, yourself. I'm not going to do here. Okay, that is you have to do yourself. Okay, so that the question will be completed. So now let's move to discuss the next topic: fundamental theorem of arithmetic. What does this theorem state? Every composite number can be expressed as the product of primes. And this factorization is unique apart from the order in which the prime factor occur. For example, 54. What is the prime factorization of 54? 54. First, e odd, once digit is 2, so it can be divisible by 2. You will get a 2, 1, 7, 27. Again, divided. It is only divisible by the 3, 9, 3. So the prime factorization of 2 is 54 is equal to 2 into 3 into 3 into 3. Clear? That is, we can write as in the exponent form, that is 2 into 3, 3 times repeated, so it will be 3 cube. So this is the prime factorization of the composite number 54. What does this theorem state? That the very important, this is, we already know how to express a very composite number can be expressed as a product of prime, we already know, but the importance of this theorem is that this also states the factorization is unique apart from the order in which the prime factor occur. That means you can write like this also, 3 cube into 2, you can also write like that, but you cannot write this 54, the composite number 54, in terms of any other prime factor like 5 or 7, etc. That is what this theorem states that. So this uniqueness of the prime factor, part of the uniqueness of the prime factorization can be used to prove many questions. And another topic under this prime factorization comes factor tree. Factor tree is the diagram used to determine the prime factors of a composite number. Let's take an example like 36. 36 divided by 2 we will get, because 2 is a prime number, so we will get here 18. Okay, then 8 divide again 18 by another 2, we will get here 9. Okay, now 9 is odd number, so it is, let's go for the next prime number which is odd, that is 3, so we will get here also 3. So what I'm going to say is that the prime factorization of 36 is equal to 2, first number is 2. Okay, first is 2 into second number is another 2, one more 2 is the, into the third prime factor is 3. Okay, 3 into another, the fourth prime factor is 3, so which we can write an exponent form, that is 2 square into 3 square. See here, this factor tree is used to determine the factors of this composite number 36. Remember, the all factors present in this tree are not prime factors, because only the left side, if you are taking like this, we will get to prime factors. But this some question used to ask like find the missing number. For example, if it is given 90, okay, 90 is given, so here it is 3 is given, here it is number is missing, and here it is 5, so you go to here it is some other number like 45 or something. So question used to ask like the find the missing number in the factor tree. Very important, even it's already learned in the lower classes, but still it is a part of our syllabus. Okay, next we can go to discuss one another kind of question that is very important, which comes under the fundamental theorem of arithmetic. The question is, check whether 6 raised to n can end with the digit 0 for any natural number n. Here we are going to use fundamental theorem of arithmetic to solve this question. So, if 6 raised to n for any n, for any n were end with the were to end with the digit 0, end with the digit 0, digit 0, it would be divisible by 10. Because, for example, whichever number you take, like 40, 40 is divisible by 10, which is equal to 4. So, if the number to end with the digit is 0, then the last digit is 0, which means it should be divisible by 10. Or any other number, if you take like 30, 30 is divisible by 10. So, if 30 divided by 10 will be is equal to 3. Okay, that is the very important criteria, that number to end with the digit 0, it should be divisible by 10. Now, that is the prime factorization of the prime factorization of 6 raised to n would contain the prime 2 and 5. But here 2 is already it contained. Because why it is 2 and 5? Because to end with the digit 0, at least 10 should be a factor of that number, or it should be divisible by 10, which means, for example, we can write it 30. 30 we can write it as 3 into 10. While the prime factorization of 10 is, again we can write 2 and 5. So if the number to end with the digit is 0, it should be divisible by 10. That means it should have the prime factors of 2 and 5. But here it's already 2 is present in 6. So we need to consider only in case of 5. Clear? 2 is already present. So it will prime contain 5. This is not possible because 6 raised to n is equal to 2 into 3 all raised to n, because 6 can only be factorized as 2 and 3. Okay, so the uniqueness of fundamental theorem of arithmetic guarantees there are no other prime factors, no other primes. That is a very important thing we have to remember, because according to the prime factorization of 6, we go to 2 and 3. And we know that by using the fundamental theorem of arithmetic, it says that the factorization of a number is unique. So there is no possibility to exceed the prime 5 in the prime factorization of 6 raised to n. So there is no natural number n for which 6 raised to n can end with the digit 0. That is very important. For example, this is logically, by taking the power of 6 we can show this one, that is 6 raised to 1 is equal to 6. What is 6 square? 6 square is equal to 36. What is 6 cube? 6 cube is equal to 216. For every exponent of 6, we get the last digit is 6 only. So this is, by writing the exponents we can say, but theoretically we prove this one. Clear? So that is very important to remember. This is a very important kind of question. Similarly, for any number we can check by using this uniqueness of the fundamental theorem. Clear? Next topic we are going to discuss, that is HCF and LCM. What is HCF and LCM? In terms of prime factorization of the numbers. That is, for any two positive integers a and b, HCF is equal to product of the smallest power of each common prime factor in the numbers, as well as LCM is equal to product of the greatest power of each prime factor involved in the numbers. And also the third relation, that is HCF and LCM of two numbers is equal to product of two numbers. This is we already learned in our classes. To understand this clearly, let's take an example that let A is equal to 24 and B is equal to 18. We can take. So what will be the factorization of these two numbers? That is, factorization of 24 is equal to 2 into 2 into 2 into 3. Okay, 4 2 into 2 4, 4 into 2 8, 8 into 3 24. Similarly, factorization of 18 is equal to 2 into 3 into 3. Am I right? That is 2 into 3 6, 6 into 3 sorry 6 into 3 18. Now, according to the definition of HCF, this is we can write in the exponent form, that is here 2 is multiplied 3 times, that is 2 cube into 3. Similarly, here 2 is ones, so 2 raised to 1 into 3 multiplied twice, that means 3 square. So HCF of the two numbers 24 and 18 is equal to, according to the definition, smallest power of each common prime factor. So what are the common factors here? Here common prime factor is both 2 as well as 3 is common. So write product of 2 and 3. Okay, that is equal to 2 and 3, and smallest power of each common prime factor. So smallest power of 2 among 2 raised to cube and 2 raised to 1 is 2 raised to 1, and the smallest power among 3 raised to 1 and 3 raised to 2, that is 3 square, is 3 raised to 1, which is equal to 6. Similarly, according to the definition of LCM, it says that LCM of 24 and 18 is equal to, what does it say? That product of the greatest power of each prime factor. That means here the prime factors are 2 and 3. Okay, 2 and 3. So greatest power of 2 is 2 cube and greatest power of 3 is 3 square. So which is equal to 8 into 3 square. 3 square is 9, which is equal to 72. So this is the LCM. So this is not necessary to follow like this. You can also use any method until and unless it is asked to find by using a particular method. Okay. Next, we can verify this relation, that LCM into HCF is equal to product of two numbers. So here HCF into LCM is equal to, what is HCF? 6 into LCM is equal to 72. That we will get it as 432. Similarly, what are the product of numbers we will get? Numbers are 24 and 18. So product of numbers is equal to 24 into 18, which is also 432. You can verify this calculation. I am not going to explain the numerical calculation. Okay, so this is all about we need to remember regarding the HCF and LCM. Question will be asked like two numbers will be given or product of the two numbers will be given, as well as LCM or HCF will be given. You have to find the second quantity. Like that question used to ask from this section. Okay, now let's discuss some questions based on this HCF and LCM. These are very important question. That is, find the largest number which divides 320 and 457, leaving remainder 5 and 7 respectively. So here, find the largest number. The question is like find the largest number. That means we have to find the HCF. So for the question number 1, the required number is HCF of 320. But the problem is that here, while it is dividing 320, it leaves the remainder 5, and in case of 457, remainder is 7. So we have to subtract that remainder from the given number first. So 320 minus 5 and 457 minus 7. That is, that implies HCF of HCF of 320 minus 5 is 315, and 457 minus 7 is 450. Okay. So HCF of 315 and 450 by using prime factorization or any other method. So you will get a 45. Now come to the second question, that is find the least number. Find the least number means you have to find the LCM. Least means it is implication for LCM. Largest it is implication for HCF. Highest. Okay, so LCM. So just to find the LCM of 35, 56 and 91, because these are the numbers it is given. Okay, find the least number which when divide 35, 56 and 91 leaves the same remainder 7 in each case. So first to find the LCM. Okay, let's find the LCM here. So 91 comma 35 comma 56. So LCM will be, okay, first let's divide by 2. So we will get here 91 is not divisible. 35 also not divisible, 56 is divisible, we will get a 2, and 28 again 2, 91, 35, 28 will be 40, again divided by 2, we will get a 2, 91 will be 91 itself, 35 and 14 will be 7. Clear? Now let's divide this by 7, so we will get 7, we will get here 13, 5, then 1. So the required LCM will be 2 cube. Okay, there are 2 is repeating thrice, into 5 is 1, and 7 into 13, which is equal to 3640. Okay, you can verify the calculation by yourself. Now the required number is, the required number is equal to LCM of these numbers. Okay, LCM of 35 and 50, 56 and 91 plus 7, because in each case it leaves the remainder 7. Clear? So we have to first find the LCM, then add the remainder to this case. So see, in both the question, first, in the first question that is related to HCF question, what we have done, we just subtracted the remainder, corresponding remainder from the numbers, then we find the HCF. First we subtracted the remainders from the number, then we find the HCF of the obtained numbers. While in the second case, what we have done, we first find the LCM, then we added the remainder to the obtained LCM. So that is very important. Clear? So what will be the answer? We will get a 3640 plus 7, which is equal to 3647. So it is very important to remember these types of question. Okay, very important. So with this question I am going to conclude this video. I will discuss the remaining portions of this chapter in the next video. So I hope you got clearly. If you have any queries, you can shoot your queries in the WhatsApp number. Thank you.